Okay, everybody. So looking at these four problems, what maybe interesting thing happened on the first question? You type it into the chat. Since there's only 10 people here today, I think there's a lot of APs going on. So people will need to type some stuff in to get the chat going. What happened on the first question? That's right. Chelsea says that the answer is the same as the second matrix. So that happens when you have this special matrix that's 1, 0, 0, 1. A matrix like that, that has ones on the diagonal going from the top left to the bottom right, but has zeros everywhere else, is known as the identity matrix. And it serves the same purpose in math as the number 1 does in just regular numbers. So when you multiply this 1, 0, 0, 1 matrix by 2, 4, 3, 5, it comes back to 2, 4, 3, 5. And you might think, well, then it must not be that important. It doesn't do anything. But the fact that this is kind of like the number 1, and by the way, for 3 by 3, it would look like this. So if you multiply that 3 by 3 matrix, sometimes we call it I with a little 3 on the bottom. And this one we call I with a little 2 on the bottom. It has to be a square matrix to be the identity matrix. Incidentally, if you were to put the 2, 4, 3, 5 on the left, in general, matrix multiplication is not commutative, but when it's the identity, it actually is. See, if I multiply the 2, 4 and the 1, 0, I would get 2. And the 2, 4 and the 0, 1, I would get 4. And the 3, 5 combined with the 1, 0 would give me 3. And the 3, 5 combined with the 0, 1 would give me 5. Now, number 2's got the x and y in there. What are the dimensions of the product? And what is the what do you get? What's the product? What is the product? And again, since there's only a few people here, everyone's going to have to do 4 times the amount of participation they usually do. Well, why don't we start with someone type into the chat, what are the dimensions? Can these even be multiplied together? And if so, what are the dimensions of the solution for question number 2? And that's right, it is going to be a 2 by 1 matrix because this is 2 by 2 and this is 2 by 1 and the 2's in the middle match up. So the answer is going to be the other 2 numbers. So it's only going to have 2 elements in it. If you take the 2, 4 and combine it with the x, y, you get 2x plus 4y. That is a single element that happens to have a plus sign in it, but it still is not violating the fact that there's only 2 elements in the answer. And the other one is 3x plus 5y. This is kind of important because if I take the 2, 4, 3, 5, wait, it was 2, I just said it, but 2, 4, 3, 5. So the opposite of multiplying is not really dividing, but to me, it's more like factoring. Like if I take 2 things, like 5 times 2, I multiply them together to get 10, and to turn 10 back into 5 times 2 is factoring. Well, it's really hard to factor matrices. If I gave you like a product of 2 matrices, it's very difficult. And even with something like numbers, there might be more than one way to do it. But if you happen to see something like this, a column matrix, and that each of the elements has 2 variables in it, we're actually able to imagine this. We could actually really see nicely, because 2x, 4y, that only happens if you have a 2 and a 4 here and an x and a y there, and this 3x plus 5y happens like that. So this is the only situation we have right now where it's feasible to actually factor a matrix into the product of 2 simpler matrices. In general, factoring matrices is very difficult, but in this special case with the something x plus something y, something x plus something y, the 4 coefficients ended up here, and the x and y end up there. Anything interesting happen with questions 3 and 4? Why don't you go ahead and pick one of them, either 3 or 4. And that's right. The third and the fourth one, when you multiply them together, you actually, for both of them, get the I2, the 1, 0, 0, 1. So that's interesting. When in like regular math, can you multiply 2 things together and get back a thing that's kind of like the multiplicative identity? Under what conditions? Like, what if these weren't matrices, but it was like just a number like 5? What has to happen for 2 numbers to have a product of 1? Or in this case, what can you say about if I say 5 times something equals 1? What is the thing in this other, what is this? And what's the significance of it? That's right. It is going to be the reciprocal, which is 1/5. Sometimes it's also called the multiplicative inverse. For regular numbers, the multiplicative inverse is the reciprocal, because when you multiply a number by its reciprocal, you get the number 1. Well, in this type of math with matrices, square matrices, or just in general, yeah, it actually does need to be a square matrix. Square matrices can have inverses. So let's take a look. Let me bring up the graphing calculator now. Here it comes, or it should be. Here we go. Okay, so we're looking at the graphing calculator. And if I say alpha zoom, this is really the easier way to make matrices. If you have an old TI-83 or an old operating system, you may not have this as an option. But the numbers were 2, 4, 3, 5. I'm going to go ahead and store that into second matrix A. And when I say second matrix A, and I put this little, actually it's the inverse to the -1, it's It's not really the reciprocal, but it is the multiplicative identity. If I hit enter, I get my answer. And you notice that is the matrix. Actually, I sometimes like to go like this and say math, enter, enter. And you can see that this is the multiplicative inverse. If I want, I could also store that instead of making it into a fraction. I can come over here and I could store it into second matrix B. And then you'll see that second matrix, or matrix A times matrix B, as we should expect, does get us the identity, just like 5 times 1/5 is 1. And it's also true, matrix B times matrix A is also 1, 0, 0, 1. Inverses are really important in this type of math. And this type of math is called linear algebra. Matrices are is the sort of type of objects we study in linear algebra, but the topic itself is called linear algebra. So the next question that you were wondering, and I'll bring back up the iPad. The next question you should be wondering is it possible to find the inverse of a 2x2 matrix? And the answer is yes. There's actually 3 ways to do it. Method 1, 2, and 3. Here's method 1. Method 1's the most sort of obvious approach, though it's not going to be the fastest way. So we're saying ABCD is the inverse. It's the thing I multiply by 2, 4, 3, 5 to get 1, 0, 0, 1. So what if I actually go ahead and multiply those 2 matrices? I get AB with 2, 3 is 2A plus 3B. That is a single element in the product. And if I take AB with 4, 5, I get 4A plus 5B. And if I take CD with 2, 3, I get 2C plus 3D. And if I take CD with 4, 5, I get 4C plus 5D. Someone type into the comments, now what? What would be the next step? How do I proceed? That's right. System of equations, 2A plus 3B is equal to 1. 4A plus 5B is equal to 0. 2C plus 3D is equal to 0. And 4C plus 5D is equal to 1. So what I have here is a system of equations, 4 equations, 4 unknowns. But it's not too bad because 2 of the equations are kind of like 2 equations, 2 unknowns, and so are the other 2. And just if I multiply this by -2, I get -4A minus 6B equals -2. And combine them, I would get 2A minus B is equal, sorry, it wouldn't be, I got confused there. This should be -4. So I would get minus B is equal to, what happened there? I'm hoping that I get as my answer, I'm hoping to get 2 for B. Let's see what went wrong there. Multiply by -2, get -4a minus 6b equals -2. I see. Add them together, get minus b, this is a b here, equals -2, or b equals 2. And then you could use that to figure out what a is, and then you could start over with these two equations and get c and d. So there is a way to do it. As you could imagine, getting the inverse of a 3x3 system of equations would be extra complicated because there would be, well, there'd be 9 equations. And that sounds like that could be a lot of work. But for 2x2, this is a viable method. It's not the fastest method. I doubt it's the method that you'll use. But it's the first method, at least the most obvious method to do. Now, before I show you the other two methods, I want to show you why it might be powerful to know what the inverse of a matrix is. So you know when you do an algebra equation like 5x equals 10, and we solve it by dividing both sides by 2. By 5, I mean. It could also be done by multiplying both sides of the equation by 1/5. 1/5 is the multiplicative inverse of 5. The multiplicative inverse times the thing itself is the identity. And 5 inverse is 1/5 times 10, which is 2. And then anything times 1 is just itself, so x equals 2. So that's what we do when we do algebra. We maybe don't think of it that way. But now let's take a look. Here I have the equation. And I think you'll think this is really neat. Remember in the warm-up, we multiplied to get a matrix. Actually, here, sorry. Let me do it. Let me not leave off a step. I'm going to change this equation into a matrix equation. I mean, I really haven't done anything yet. It's just if this really equals 14 and this really equals 19, then the 2x1 matrix that has 2x plus 4y as its first element, row 1, column 1, and 3x plus 5y as row 2, column 1, that should equal the 2x1 matrix with 14 as row 1, column 1, and the 19 as row 2, column 1. But this 2x1 matrix can be factored. As we saw, we multiplied this together in the warm-up to get this, but we can go in this other direction. Now notice how similar this looks to something like 5x equals 10. It's a thing times a variable thing equals another thing. So in the 5x equals 10, well, yeah, we could divide by 5 if we're allowed to divide. If we're only allowed to multiply, we would multiply both sides by the multiplicative inverse of 5. And that's exactly what we're going to do over here. On both sides of the equation, I'm going to put this little 2, 4, 3, 5 with an inverse. But if I do it on the left side, I have to do it on the right side also. Right side of the equation, that is. Now, because matrices are not commutative, if I put the 2, 4, 3, 5 all the way on the left if I put it on the left side here, I have to squeeze it in between the equal sign and the 14, 19 there, because so it's multiplying on the left. Because if I multiply this one on the left and this one on the right by putting the 2, 4, 3, 5 after the 14, 19, that might not balance it out because it doesn't necessarily, it's not commutative. Now, what happens to this 2, 4, 3, 5 inverse times 2, 4, 3, 5 inverse? 2, 4, 3, 5 inverse times 2, 4, 3, 5. What's the product of just those two things? That's right. 1 in the sense of matrices, which is 1, 0, 0, 1. Now here I still have the 2, 3. It's just 2, 3, 4, 5. They just no 2, 4, 3, 5. I keep, I don't know why I'm having such trouble remembering that. And what can you say about this left-hand side? 1, 0, 0, 1 times this x, y, this 2 by 1 matrix. It's kind of like this here, 1x equals 5 inverse times 10. That's kind of where we are in this problem. What's the product of this thing that has a box around it now? Well, the left side's the identity. It is, the left side's the identity. So what does that make the product? Yes, it just becomes this xy thing. Now we're at our last step. Now we can dig up, remember from before, we worked out that the inverse of this 2, we can replace the 2, 4, 3, 5 inverse with negative 5 over 2, 2, 3 over 2, negative 1. Now that might have taken a lot of work to get the inverse, but let's just say we have it for whatever reason. And now I finish up the problem. This is a 2 by 2. This is a 2 by 1. So these match up. So we can multiply them. The answer is going to be a 2 by 1 matrix. And if we actually do it out, first row, first column, negative 5 over 2 times 14 is negative 35. I imagine the 2 canceling out with the 14 to become 7. Negative 35, 2 times 19 is 38. Negative 35 plus 38 is 3. And the other element comes from multiplying this by this. 3 over 2 times 14 is 21. Negative 1 times 19 is negative 19. 21 and plus negative 19 is 2. So the answer to the question is x equals 3, y equals 2. Well, this is quite a lengthy way to solve this equation. But it is a way, and there might be some situations where, like one situation where I could imagine, you might say it takes so much work to get the inverse. We don't have a shortcut yet for getting the inverse, but it seems like the bottleneck of this process, the reason you wouldn't want to do this method is because getting the inverse that you need to do the last step is its own very lengthy process. But let's say I spent time, a few minutes, and I figured out the inverse of 2, 4, 3, 5. Well, once I have it, I can answer questions besides this one. I could also answer any question. Imagine I had, 2 other numbers here. Or suppose I had just all kinds of, I had to, for whatever reason, do so many problems that all started with 2x plus 4y equals something and 3x plus 5y equals something. And I had all these equations to do. Well, each one can be accomplished, like this one can be accomplished by doing xy is the inverse of the coefficient matrix times the matrix made up out of the 2 things after the equal sign. And since this thing's already calculated, I could just one by one solve questions of this time. So maybe it's a lot of work to get the inverse if you're only doing one question, but if we had to do 100 questions that all had the same coefficients here, getting the inverse one time and then using it over and over might save us time in the long run. So method number one for finding, so I hope I've shown you that finding an inverse is, potentially a useful thing. If you have a graphing calculator, let's go back to the graphing calculator. And oops. Oh, there. I've lost all my stuff. Hold on a second. Where's everybody? There. So if I have a graphing calculator and I wanted to solve a system of equations, well, we had the RREF shortcut. There's nothing really faster than that, but it is pretty fast still. If I have that equation that we had before, and I say alpha zoom 2 by 2, and I just say 2, 4, 3, 5 inverse multiplied by alpha zoom, I'll make a 2 by 1. There's 2 rows, only 1 column. And that one was 1419. Then out would come, the 2 answers to the question. So we have yet another way to solve a system of equations. I know the RREF was like the fastest way, but this is another way to do it. Okay, let me go back now to the iPad. Well, so far, the only method we have for finding inverses is, it was lengthy. Well, I have a second way of finding inverses. Unfortunately, this second way is even longer. But the second way is going to lead us to a formula, and the formula is going to end up being the shortcut. So we have one way that works nicely, but here comes the second way. The second way is kind of like, it works like this. If I had the number 5, and next to it I put the multiplicative identity, and I thought, okay, what thing do I need to do to the thing on the left to turn it into the identity? And the answer is multiply by 1/5. Well, the thing that turns a number into the identity will turn the identity, if I do the same thing to that number, into the inverse. So this is the original number, and this is the inverse. Because if I undo it, this would turn into 5 and this would turn into 1. So kind of like it's related to that. Well, the same thing is going to happen for this kind of annoying second method. Well, the first method would be really hard for a 3 by 3 system because you'd have 9 equations. This other system, this would also be hard, but maybe not as hard. But here it goes. We are going to systematically, over a period of 4 steps, turn the matrix on we make a big matrix that's 2 rows, 4 columns. And this line down the middle, it's not really necessary to have that line there, but the idea is that I have a 2 by 2 matrix here and an identity matrix next to it. And I'm going to systematically turn the thing on the left into the identity, into the thing on the right. And the same steps are going to be done to the thing on the right, and that's going to turn the thing on the right into the inverse of the thing on the left. And the first step is 1/2 of row 1. So it becomes 1, 2, 1/2, 0. Now that I have a 1 here, my next step is to make that a 0, just like you do with Gaussian elimination. Does someone want to tell me what the row operation is that's going to turn this 3 into a 0? This is from the lesson 2 lessons ago, where we did elimination. Yes, minus 3R1 plus R2 goes into R2. Minus 3R1 plus R2. Yes, you don't have to say goes into R2 because it always goes into that. So the first row does not change. The second row, minus 3 times 1 plus 3 is 0. Minus 3 times 2 is minus 6 plus 1 plus 5, sorry, is negative 1. Minus 3 times 1 half plus 0 is minus 3 halves. And minus 3 times 0 is 0 plus 1 is 1. Step 3 is to make this into a 1, which is done by doing minus R2. And will someone type in, what is the row operation that will turn that 2 into a 0, which will then complete the process? Very close, other way around, the minus 2 R2 plus R1, because it's the second row that's being multiplied. So minus 2 R2 plus R1. The bottom row doesn't change, but the top row, 0 times negative 2 plus 1 is still 1. 1 times negative, or negative 2 times 1 plus 2 is 0. Negative 2 times 3 halves is negative 3. Negative 3 plus 1 half is negative 2 and a half, or negative 5 over 2. And finally, negative 2 times 1 is negative 2 plus 0 is negative 2. And as you can see, the steps that turned the original into the identity, those same steps turn the identity into the inverse of the original. Oh, is there a next, so mention, is there supposed to be a, did I lose the negative 1? Where was that going to come? Over here? Thank you. That makes this into a plus 2. Okay. So now we have the challenge question. I'm going to put you into groups for this. What if because there's going to be a formula that gets this inverse really quickly. But to derive the formula, what I want you to do is do the 4-step process, but use A, B, C, D, just generic variables, and see what you get. I'm going to put you into, there's only 11 people. I'll put you into groups of 3 if I'm able to. Let me pause the recording. Okay, everybody, there were some complications with the breakout rooms, and I'm sorry some people weren't able to get into the breakout rooms. I'm going to show you that it starts off by, if you divide everything by A, you end up with this. And then if you multiply the top row by negative C and add it to the bottom row, you start getting some pretty ugly expressions. But when it's all said and done, and you could write this down, it becomes a formula. When it's all said and done, you get this expression. Now notice all the answers are fractions, but the denominator of all of them is this mysterious AD minus BC. And the numerators are just the 4 numbers from the original matrix, except the A and D swapped places, and the B and C stayed in the same place, but became negative. So watch what happens if I apply this formula to this process. The d and the a are the numerators, so 5 over and 2 over. And the 4 and the 3, those stay as the numerators, but they become negated. And all the denominators are AD minus BC, which is 2 times 5 minus 3 times 4, which is negative 2. As you can see, that turns into the answer, negative 5 over 2, 3 over 2, 2, and negative 1. So for sure, this formula is going to come in handy. And also for sure, being able to find the inverse of a matrix is going to be an important thing. And we can see, at least from today's lesson, we just did that question, we can see from today's lesson that knowing the inverse of this would enable us to solve a question like 2x plus 4y equals something and 3x plus 5y equals something else. We'd be able to answer that question real easily because we could say that xy is equal to 2, 4, 3, 5 inverse times. I'm just going to put an a and a b here. Okay, so what we learned today were 3 ways to find the inverse, and we learned one. There are other applications of inverses, but I really like this application of inverse because it relates to systems of equations, and it's so similar to what we do when we do 5x equals 10, multiplying both sides by 1/5. I like that there's sort of this parallel idea going on between the algebra we learned a long time ago and between systems of equations that we've been working on and using matrices for them. And here I have on the screen the main sort of thing that we learned today. Right here, to get from here to here, required being able to find the inverse. Okay, so that's going to do it for today. Does anyone have, I know there's a lot of APs going on, so only a few people here today, but I'm glad whoever could come came, because this unit, the linear algebra, it's going on for another couple of weeks, and you want to stay on top of it each day so it doesn't get too difficult. Let me pause the video.